When an educator assigns a rigid 85% or an examiner records an IQ of 126, the assessment feels final. The ink implies exactitude. Both educators and parents routinely treat these single numbers as biological facts. We project certainty onto a static score, assuming it perfectly maps to a student's cognitive ability. Psychometricians view this perceived precision as a dangerous illusion. A test is a localized snapshot, subject to internal flaws and external variables. A single test score represents a range of possible truths, rather than a fixed point of mastery. The written number is simply the center of a probability curve. Making high-stakes decisions based on that range, like holding a student back or admitting them to advanced programs, requires mathematical proof that the assessment consistently measures what it claims. Ignoring this underlying uncertainty makes it nearly impossible to defend the instructional decisions that follow. Context dictates the mathematical validity of a test. No exam is universally reliable in a vacuum. This principle is codified in the 2014 Standards for Educational and Psychological Testing. This document serves as the definitive rulebook for assessment creation and evaluation. The 2014 standards shifted the conceptual vocabulary of the field. They replaced the generic term reliability with the more rigorous mandate of reliability/precision, denoting the score's consistency across repeated applications. Proof of consistency must be provided for the exact intended use of the score. The statistical evidence required for a high-stakes graduation decision is vastly different from the evidence needed for a weekly quiz. Mathematical precision always belongs to the specific decision being made, rather than being an inherent property of the test itself. Before calculating that mathematical precision, test designers must prioritize their instructional targets. Many designers attempt to measure a student's mastery of 25 different instructional targets using a 25-item test. Allocating only one item per concept yields highly superficial data. A sample size of 1 cannot support accurate inferences about a student's covert abilities. Sound design requires deeply assessing a modest number of prioritized outcomes. Clustering enough items under a few specific targets allows the designer to isolate a signal from the noise. Expert W. James Popham notes that test creators must have the courage to prioritize. Attempting to cover everything guarantees that nothing is measured well. Ensuring an adequate concentration of questions per target allows us to measure a test's consistency across 3 distinct factors. Without a sufficient cluster of items, no statistical formula can salvage the test's reliability. Bad design inevitably creates bad data. The first vector of consistency is the metric most frequently cited in commercial testing: internal consistency. Internal consistency measures item homogeneity. It determines whether all the individual questions designed to measure a single variable, like reading achievement, are doing the same measurement job. Test publishers favor this metric because it is the only vector of reliability that can be calculated from a single administration of a test. This text identifies the specific statistical formulas used to calculate this internal homogeneity. The Kuder-Richardson procedures are applied to dichotomous items, those scored simply as right or wrong. For polytomous items with multiple score points, like essays, analysts use Cronbach's coefficient alpha. A cautionary trap is seeing a high internal consistency score and assuming the test is reliable for all possible purposes. A 0.90 internal consistency coefficient reveals nothing about whether a student's score will remain stable if tested again, or if they take a different version of the exam. Relying solely on internal consistency provides a false sense of security, rendering longitudinal instructional decisions statistically invalid. Stability requires Vector 2, test-retest reliability. This procedure involves administering the same test to the same students a few weeks apart, ensuring no significant instruction occurs in the interval. While test makers can calculate a correlation coefficient to show stability, this table illustrates a more practical approach for classroom decisions: classification consistency. Instead of comparing exact numerical scores, this tracks the percentage of students sorted into the same performance buckets, like exempt versus requires further study, on both testing days. Vector 3, alternate form reliability, tests the equivalence of 2 different formats of the same exam. This vector is the standard for high-stakes environments. If a student takes a makeup graduation exam, the forms must consist of different questions, while the statistical challenge remains identical. These three vectors are separate hurdles. Internal consistency tests the items against each other. Test-retest checks stability over time. Alternate form ensures fairness across variations. Educators must match the type of reliability evidence to the specific assessment decision they are making. Applying the wrong vector leads to choices based on phantom data. Group metrics eventually meet the individual. How did these abstract reliability coefficients affect a single student's score? We quantify individual uncertainty using the standard error of measurement, or SEM. The first variable, SX, represents the standard deviation, the spread of test scores across the entire group. The second variable, RXX, is the test's chosen reliability coefficient. The mechanics of the formula dictate a strict inverse relationship. As the reliability of the test goes up, the standard error physically shrinks. The SEM practically estimates how much a specific student's score would vary if we could subject them to the same assessment procedure repeatedly. This calculation provides the bridge between theoretical test reliability and classroom reality, replacing the illusion of absolute precision with a measurable margin of error. The stakes are clearest on state accountability tests, which use rigid cut scores to classify students. Consider a hypothetical student who scores exactly 44, the razor's edge of proficient. If the test has low reliability, the large SEM creates an error bracket bleeding heavily across the cut line. With a large error margin, this student's true score could reside in the basic zone, making their label a statistical coin toss. High test reliability acts as a protective shield. The margin shrinks, keeping the variance firmly within the proficient classification. Shrinking the SEM requires demanding rigorous reliability and precision data from test publishers and school districts. Properly managing this math provides the statistical confidence needed to classify students fairly and target their interventions accurately. Professionalism requires mathematically respecting the margin of error, ensuring the data protects the student instead of mislabeling them.